Okay, let's go ahead and talk about nuclear radiation and decay. First, let's talk about the four fundamental forces of nature. You may have heard of some of these before, such as the force of gravity. Okay, gravitation is something we see all the time, and it explains how objects fall towards each other, objects with mass. But we have three others here. We have the force of electromagnetism, which explains how electrons are kept within the atom and they're attracted to the nucleus by opposite charges. We have the weak interaction, which helps to explain how atoms can decay. And we have the strong interaction, which is what keeps nuclei together. Because we remember that protons have positive charges, and you would expect them to repel. But because these neutrons are here, there's this strong interaction, this force that keeps them together. Okay, so these four forces together, they help to explain all of the forces found in the universe. And in fact, physicists are working tirelessly on coming up with a grand unifying theory, also known as GUT. Okay, the grand unifying theory to put all of these together and have one equation. Okay, the theory of everything. So that's some exciting stuff going on in physics. Let's talk about nuclear stability. Okay, there's a particular ratio of protons to neutrons that's ideal in creating a stable nucleus. If you remember that simulation that we did a few weeks ago, certain nuclei can become unstable if this ratio of protons to neutrons is off. Okay, so there is some particular ratio that's necessary. Each element has a different and unique ratio. Okay, and when this ratio is disturbed, certain types of decay can occur. All right, so let's look at this graph here. If you see this line here, that would be a 1-to-1 ratio of neutrons and protons. And there's types of decay that can occur when you plot this on a graph. Okay, so a stable nucleus would follow this black curve here, and on either side of this curve, you can have different types of decay, and we're going to talk about those next. So, types of radiation. There are three main types of radiation we will talk about. So if you have a radioactive material here, and it's contained inside of a lead block to prevent it from reaching you, you can see that it would emanate out. And if you had an electric field, this is sort of similar to J.J. Thomson's experiment, where he had a magnet here with two poles, positive and a negative. You can see the effect on these particles. So beta particles would be attracted to the positive pole, alpha particles would be attracted to the negative, and gamma particles here are not attracted to either. So we can deduce from this that beta particles carry a negative charge because they're attracted to the positive, and alpha particles contain a positive charge because they would be attracted to the negative charge. Again, gamma rays do not have a charge and they're unaffected by this electromagnetic field. The penetrating ability of these three varies pretty significantly. So alpha particles are by far the largest, and what they are is essentially the nucleus of helium atoms without the electrons, right? So they carry a positive charge, and they will be stopped by simple paper, okay? So they're not terribly difficult to avoid. Beta particles, however, can go through paper, and they would be stopped by aluminum, for example. And then gamma radiation, which is simply pure electromagnetic radiation, it's energy. It can go all the way through and penetrate lead. Okay, so you would need quite a large barrier to stop gamma rays. So in order of penetrating ability, gamma rays are the best, beta particles are second, and the worst would be alpha particles. Let's talk about alpha decay specifically. So like I said, we have the helium nucleus, which has 2 protons and an atomic mass of 4 that comes from all 4 of these particles. Okay, that's what an alpha particle is. And we saw this with Ernest Rutherford's gold foil experiment, if you remember that one. Alpha particle emission occurs somewhat like this. If you had a plutonium nucleus, it can emit an alpha particle and turn into something completely different. Here we have uranium 235. Okay, uranium is always number 92, but it has certain isotopes, and in this case, it creates the uranium 235 isotope from plutonium 239. This is a unique thing that alpha particles can do when they are released from plutonium. Notice that we have an equation of sorts down here. If you take 235 and you add 4 to it, you will get 239. And if you take 92 and you add 2, you will get 94. So this is an equation that's set up. Think of this arrow as an equal sign for now. Everything has to add up from one side to the other, and that is important as we move on. Okay, beta particle emission is the next one. Think of neutrons as the combination of a proton and an electron. Okay, so neutrons have no charge, protons have a +1 charge, and electrons have a -1 charge. Okay, electrons also do not have mass, so it would make sense to think of neutrons as the combination of a proton and an electron. Okay, so that's what I have shown here. Go ahead and write that down and make sure you understand that. Let's look at beta particle emission for an example. If you have a neutron, okay, it has 0 protons, and it has the atomic mass of 1 here. On the left side of this equation arrow, and on the right side, we have to be able to add it up. So if we're going to emit a beta particle, which is essentially just an electron, okay, we have to be able to add it up. So a -1 plus 1 will give you 0, and 0 plus 1 will give you 1 here. And a proton, remember, is what the nucleus of hydrogen is. So it has an atomic number of 1 and a total mass of 1. So you can write proton in this notation like hydrogen, just the hydrogen nucleus. Okay, so take a moment to try to understand this. It's a little bit confusing. Neutrons act as both the combination of a proton and an electron. What beta particle emission would look like is shown here. We have carbon-14, an isotope of carbon, and it emits a beta particle right here, this electron here, and it forms nitrogen-14. Okay, so let's look at how this happens. if you emit a beta particle, it's all about making sure the right side equals the left side. So a -1 plus 7 will give you 6. And then a 0 plus 14 will give you 14. So, for example, if you didn't know what the result here was, let's pretend like this was not available to you, you should be able to work backwards and say 6 equals something plus a -1. And that something would have to be 7, right? So that would lead you to know that the atomic number is 7, and that leads you to nitrogen. So with beta particle emission, you can take a carbon-14 isotope and create nitrogen-14 from it. Okay. Let's talk about something else that's related to beta decay. This is called positron emission, also known as beta plus decay. So beta minus decay is what we just spoke about here. And the result of this is an electron, right? So that would be the beta particle and an antineutrino. Okay, we won't get into exactly what that is, but it's basically massless and it's another subatomic particle. Beta plus decay, however, will give you the opposite. Okay, so if you have beta plus decay, you can go from carbon 10 to boron 10. And as a result, you're taking 6 protons and you're making it 5 protons and then 4 neutrons, to 5 neutrons. And instead of creating this electron, you're creating a positron, and instead of an antineutrino, you're creating a neutrino. But let's not get bogged down too much in this. I just wanted to mention it because your book does. Okay? Again, if you are confused about any of this, please let me know, and realize that there are lots of videos on YouTube and resources to help you out. Let's talk about gamma radiation, which I feel is the easiest for students to understand, simply because it's high energy photons, or particles of light. And as we talked about at the beginning of the year, light does not have any mass. So that would lead you to believe that mass and the atomic number remain unchanged as you emit gamma radiation. So let's look at this. Gamma radiation is typically accompanying other types of radiation. So what we have here is gamma radiation accompanying alpha decay. So we have thorium-230 that decays into radium-226 by emitting an alpha particle and a gamma ray. Okay, this is usually omitted in writing nuclear equations because it doesn't change anything. However, for the sake of learning this, we need to include it here. Notice that there are 2 zeros here, one representing the atomic number, which of course is 0 because there are no protons, and the atomic mass, as well as 0 because there are no protons or neutrons. If we add up all of the numbers, we have 0 plus 2 plus 88 gives us 90, and 0 plus 4 plus 226 should give us 230. So all of the numbers are accounted for, and the left side equals the right side. Okay, go ahead and try these on your own. I'll let you pause the video, write these down, and try to fill in these blanks here. So there's a blank here, 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 and here. And then we'll go over the answers together. So I hope you took some time to do those. Let's talk about these answers. As you can see here, if you start with copper 66, and you end up with zinc 66, it looks like the atomic number increased by 1 here. So that means that on the right side, we would have to have some beta decay, because -1 plus 30 will give you 29. And that's the only type of decay that we can fit there. Let's look at the second one. If we have bismuth 214 and it creates polonium 214, it looks like our atomic number increased by 1, and we do have shown here that it's beta decay. The only other thing that could fit here would be gamma decay as well, gamma radiation, because it doesn't add or subtract from either of these numbers, the atomic number or the mass number. Okay, the third one, we have thorium 232. And on the right side, we have radium 228 and an alpha particle. So let's make sure that this works. If we have 2 plus 88, that should equal 90, and it does. 4 plus 228 is 232. So that one checks out as well. And the last one. If we have radium 226, and we have this blank, but we know that we have alpha decay, we need to fill in this blank with something that will complete this equation. So I would prefer doing the subtraction. 88 minus 2 will give you 86, which is radon, and 226 minus 4 will give you 222. So the isotope of radon here in this particular case is 222, and the math checks out there as well. So that's how you would complete nuclear equations. And I have a practice down here. It's called the uranium decay chain practice, which will give you even more exposure to this. And I will also have a video showing the key for that one. So we made it through. Go ahead and watch this video again if you need to, and let me know if you have any additional questions.